Alright, ladies and gentlemen, we're going to look here at our copper solid being placed in nitric acid. Might have been solid copper powder placed in 8 molar nitric acid, making blue copper nitrate solution and brown nitrogen dioxide gas plus water being emitted. Now this reaction you might recognize from one of the labs we did earlier on in this year. So let's see if we can balance this reaction. So the first thing to identify here is the half reactions. So to identify the half reactions, we've got copper here, and copper here has oxidation number of 0, and copper here is going to copper nitrate, which is Cu here, and the charge on this is a 2 plus because of the 2 nitrates, so you have a +2 oxidation number for the copper. So it definitely looks like the copper is being oxidized. Now the question is determining what is being reduced. So our options are, we've got the HNO3 on the left, something in here. Okay, so HNO3 here, that has a positive oxygen as a 2 minus, and there are 3 of them. So that's -6 plus 1 is -5, so nitrogen has to be +5. So nitrogen here has to be a +5 charge oxidation number, this hydrogen +1. Now, the first one here, when you go NO3, well, you look over here at this end. What's that charge? Well, here, the nitrate ion has a negative net charge, and there are three of those. 3 times -2, that's -6, that has to be +5. So the nitrate to nitrate is not changing. Okay. The oxygen over here, though, that's 2 minus. The nitrogen, in order to make this correct with the oxidation number, this one has to be +2. So the oxidation number here, 2 plus, the oxidation number here is +2. So our change is happening when the HNO3 is going to NO. Now in this particular reaction, we also have water being produced. So we can consider that and how that plays a role here with the HNO3. And we've also got H here, which is a hydrogen ion. So to write that simpler, we take our H plus, separate that from our NO3 minus, and that makes our NO. Okay. And here is our initial oxidation reaction. And this one is going from a +5 to a +2. So that is being reduced. So that's oxidized, and this is being reduced. So we have our half reactions. The next thing is to balance out the atoms other than H or N. H or O. So all of these are currently balanced. Here we got 1 N, 1 N, 1 H, Cu, Cu. So now we balance out the O's. On this side we've got 3 O's, on this side we only got 1. So we're going to add 2 waters to this side here. So we add 2 waters to this side. 2 times 2, that should be 4, so there should be a total of 4 H pluses on that side. So 4 H pluses, we've got our NO3 going to NO plus 2 H2O. Now when we add 4 of the H pluses on this side here, that allows us to balance that reaction out. The next step we would need to do is we need to get the electrons. So we've got the H's, the A, and the O's done. So the next step is the electrons. There's 2 electrons here to make that neutral. And in this case, we have 4 positive minus 1, that's 3 positive, so we need 3 electrons on that side. So now we have the electrons, at least balancing the charge on each half reaction. Next step is to take each of the half reactions and equal out the electrons. So we got 2 and 3, so we multiply this by 3, this by 3, that by 3 is going to give us 6 electrons, and then this by 2, so that gives us 6 electrons. That gives us 8, that gives us 2, that gives us 2, that gives us 4. So last step is to, again, add these up because it's an acidic solution. We've got 3 coppers plus 8 hydrogen ions plus 2 the nitrate ions plus 6 electrons. And on this side we got 3 copper plus 2 NO plus 4 waters plus 6 electrons. So the 6 electrons cancel, and we're left here with a balanced chemical equation here that shows our nitrates are 6 electrons plus 8 here. So here we have what would be called a balanced redox reaction. Now the only challenge though is in this case we have 8 H's, but we don't have 8 NO3s. Okay. So what we can do here is the last step is we need more of these NO3s on the left side in order for this to be balanced with the nitrates on each side. So right now the equation is balanced, but again we don't have all of the nitrates included. So what we can do next is if we add 6 more nitrates here, okay, the spectator, so we can add 6 more nitrates here to give us a total of 8. So we're going to have 6 nitrates here to give us a total of 6 on this side and 6 on this side. So that here would show our balanced chemical reaction. And the way to write this here with our coefficients is we would have the following, showing the coefficients including. So if we look here at our reaction down here that we just made, in order to get it back into what's called the molecular form, that's the one that's shown up here. So this is called the molecular form because it includes spectators. We added 6 nitrate spectators to the left and to the right to make sure that the nitrates were balanced. So here we would have a 3 in front of our copper, an 8 in front of our nitric acid, and then a 3 in front of our copper nitrate. 3 times 2 even is 6 nitrates. Here we've got 8 nitrates. Okay. And they don't balance, of course, because of the redox, because we have 2 of those and 4 of those. So there's the 2 additional nitrogens. So this here was from the first lab we did of the year, the copper cycle lab, and we were not able to balance it then because we did not know oxidation reduction. And we did not know that the electrons could be transferred, and changes in oxidation state could give us a molecular equation looking like this. The net ionic equation that's down below, the net ionic equation without the spectators, is usually how chemists represent this type of reaction. But when we think of the molecular viewpoint, you still have nitrates floating around in solution before and after, so that's why they're included in the molecular explanation. So this is how to balance copper and nitric acid, making blue copper nitrate, nitrogen dioxide, brown gas, and liquid water. That's chemistry with Mr. Christopher. I hope you have a great day. Talk to you later. Bye-bye.